You know how Stephen Hawking said, the best evidence we have that time travel is not possible and never will be, is that we have not been invaded by hordes of tourists from the future. But what if these tourists come to our time, but they do it secretly? You may even have met one of them. Let's see the most famous time travelers. Meet Orin. He's a cyborg who came to us from the year 2050 to stop the coming end of the world. In 2020, he appeared on a TV show where he said the whole world was inside the Matrix. Then he hit the headlines and gave an interview to a popular YouTube channel. As proof that he's a cyborg, he demonstrated his robotic voice, which can be made in a simple computer program. He also called himself We because he declared himself a collective consciousness that had come to save humanity. Orin became famous for his predictions about the near future, but it turned out that many experts had already announced these forecasts earlier. He also said that a huge corporation was suppressing humanity, and we were inside a complex computer simulation. If we don't improve or care for each other and nature, the end will begin in 2050. Orin no longer appears on major shows, but he has a small fan base of people who love all sorts of fantastic theories. Another time traveler is Archin, who came to us from 2045. There was an interview with him on YouTube where he shared some details about the future of the US, after which the video went viral and hit the lines in many newspapers. Archin reported that the last official president of the country would be the daughter of Martin Luther King III, and she would become the greatest US president in history. Another exciting event that Archin announced is supposed to happen in 2028. He said that people would learn about the existence of extraterrestrial civilizations. He added that these creatures wouldn't come from outer space. The traveler also noted that the world would switch to a single digital currency and all cash would disappear. Of course, no one believed him, so the experts conducted a lie detector test. And Archin successfully passed it. He said that he had a chip in his hand to facilitate time travel. An extraterrestrial civilization would arrive on Earth in 2028, and in 2045, people would be closer to robots. The lie detector didn't state that Archin was lying, but this doesn't mean he told the truth, since the device can be deceived with the help of special training. In any case, in 2028, we will find out whether Archin was right or not. All these time travelers arrive in the past and, for some reason, don't use knowledge from the future. What would you do if you could go back 50 years? Perhaps you would invest money in shares of some young company that will become a big, expensive corporation. In that case, everyone would believe that you really came from the past. And by the way, one guy did it. He invested $800 in the stock exchange and made $350 million out of it. This guy's name was Andrew Carlson, and he hit a big jackpot in 2003. However, he didn't manage to enjoy a rich life because the FBI came for him. Andrew sold some stocks and bought others, and did this very successfully. Thus, in a few months, he became a millionaire. The Securities Commission couldn't believe in such coincidences, so it called the FBI. During the interrogation, everyone was sure Andrew would begin to justify himself and say he was lucky. But instead, he calmly replied that he came from the year 2256 with the help of a time machine. Of course, no one took it seriously. But when the FBI started looking for information about this man, they found nothing. Andrew Carlson had no documents. He was not in any database. He just appeared out of nowhere and started making a lot of money. He was interrogated for about 4 hours, and he behaved pretty calmly. It seemed as if he was telling the truth. However, he didn't tell them the time machine's location. When the press found out about this man, he immediately became a celebrity. Well-known news sites began to write about Andrew Carlson. Articles have appeared in Japan, Australia, Germany, the UK, and other countries. And of course, journalists started calling the FBI to find out more details about this guy. And the FBI told them that the whole story was fiction and that there was no Andrew Carlson. Information about him appeared on an internet resource known for its fake news. At some point, the article about the time traveler somehow got into Yahoo, where it went viral. So, as we see, all statements about time travelers are either fiction or a lie. Conversations about such travels appeared thanks to fantastic films and books. Pop culture has greatly influenced this fantastic concept and created several theories claiming that time travel is real. And some people believe that, especially those who are far from science. But what do real scientists think about this? Are such trips really possible? Let's try to find out. Scientists say yes, time travel is real because we're now traveling in time. Time is moving forward and we're moving with it. We call it a journey. But if we need to get into the future or go back to the past, everything is much more complicated here. Remember Einstein's little theory of relativity? It says that time moves relative to the observer and has no constant value. To understand better, here's a simple example. 10 hairs on your head. Is it a lot or a little? 10 hairs in a bowl of soup. Is that a lot or a little? Everything is relative and depends on the conditions. The same thing happens with time and space. If we move at a tremendous speed, close to the speed of light, then time slows down for us. The perception of time becomes different for a person who's running and for one who's standing still. If we're near some heavy object, let's say 1,000 times heavier than the sun, then the time next to this object also slows down, thanks to its strong gravity. In this sense, time travel is possible. If you're an old person and meet your friend as young as he was 50 years ago. Why are you so young? Oh, I've been flying in space at a tremendous speed all this time, that's all. But this doesn't mean that this friend just sat on the ship for 50 years and didn't age. No, time was different for him. 10 years for you on Earth is a long period of time, but for him, these 10 years passed like half an hour. Gravity and speed bend time. For this reason, astronaut Scott Kelly, who spent a year and a half in orbit, became 5 milliseconds younger than his twin brother after coming to Earth. All this time Scott spent inside the ship flying in orbit at high speed, and he was also further away from the gravitational center of the planet. So, time was slower for him by 5 milliseconds than for his brother. Objectively, time always runs at the same speed, but its speed changes inside the perceptions of different observers under different conditions. That's what the theory of relativity is about. But what about jumping into the future or the past, like in movies? Wormholes will help you with this. This is something like tunnels that pass through space and time and can connect different time segments in different places in the universe. They are like cheat codes that can break the laws of the universe. Wormholes are elusive, have different sizes, are unpredictable, appear in space, and vanish. But their main problem is that wormholes only exist in theory and sci-fi and have never been noticed in our universe by scientists. It looks like there's a terrifying crack in our understanding of the universe. Scientists have compared how fast the universe expands. 2 methods, 2 measurements, completely different answers, and no one knows why. As they dive deeper into this, a new terrifying idea came up. Our entire universe might be spinning. If that's true, it changes everything we know about space, time, and even how the world will end. To understand what's going on, let's talk about how our universe expands. How exactly is it expanding? Into what? We first noticed this about 100 years ago. For many years, people thought the universe was eternal and unchanging. Then came Edwin Hubble. He observed the universe in the telescope and realized the light that came to our planet was coming from galaxies that were moving farther away from us. The galaxies weren't sitting still. The whole universe was moving. And this became one of the most revolutionary discoveries in history. The movement started with the Big Bang. It happened about 13.8 billion years ago. The entire universe, all matter, energy, space, and time burst forth from an incredibly hot, dense point. The bang sent a shockwave, giving all the things and particles their initial boost. That's how they started drifting away from each other. The thing is, they weren't drifting away into open space. No, they created space themselves by drifting. Let's say you're holding a balloon. You draw some dots on it. You start blowing air into it. The balloon gets bigger and bigger. And every dot on its surface moves away from every other dot as the balloon expands. As dots move apart, they basically create space between them by moving away from each other. So the universe isn't expanding into some mysterious space. Space itself exists only within our universe, born between moving dots. The Big Bang boost was so strong that the universe started expanding incredibly fast. It's hard to even imagine. If you were chilling and watching this from the side, it would seem like the entire universe appeared out of nowhere in less than a moment. You wouldn't even hear it because there's no sound in vacuum. There would be nothing. Then you would just blink and bam! The world is everywhere. That bang was so huge that the universe is still expanding from it even now. Even billions of years later, it's space itself that's stretching, with every point on it drifting farther and farther away, including us. We're just moving at a more gentle pace, sort of. So when we figured out everything was expanding, the next question was, how fast? Turns out the movement speed is different for different galaxies. We noticed that the closer things are to us, the slower they drift away from us. And the farther a galaxy is from us, the faster it appears to be moving away. And they're moving constantly. We say, for example, this galaxy is 100 megaparsecs away. But since the galaxies don't actually stay in one place, that means this galaxy is moving at a speed about 4,300 miles per second away from us. If the distance doubles, then the galaxy's speed doubles. So, for example, if a galaxy is 1 million light-years away, it will move away from us at a speed of about 46,000 miles per hour. 2 million light-years away? Double it. Now it's about 92,000 miles per hour. 10 million light-years away? Almost 500,000 miles per hour. Scientists call it Hubble's law. Speed is equal to Hubble constant multiplied by distance, and the Hubble constant is the exact magical speed number that we keep adding up every time we move 1 million light-years farther. So, the Hubble constant is basically the rate at which expansion happens. But there was a problem. A problem that seemed tiny at first, but it was actually hiding a huge disaster. When we measured Hubble constant using 2 different methods, for some reason, we got different results. The first method was to calculate it based on what we see around us right now, today. Different stars, galaxies, their light and brightness. In certain stars, brightness changes in predictable ways. Huge star booms, like supernovas, act like cosmic lighthouses. We know how bright they should be, and thanks to that, we can calculate their distance and speed. It's all clear and simple. But then, scientists tried something totally different. They often used this trick. To figure out how the early universe behaved and then simulate everything from the start, it's like creating your basic characters in Sims and letting them do whatever, hoping that they'll do things in predictable ways and not pull off something wild. We can guess what the early universe looked like because we can still detect the faint afterglow of the Big Bang. We have ultra-precise telescopes that allow us to find an ancient, very first light and very first traces of energy that were born in our world. This post-Big Bang afterglow is literally filling up the entire universe. It's just scattered around like some dinosaur fossils. So we take these fossils and recreate the entire dinosaur based on them. And when we measured what the Hubble constant should logically be, based on how our universe was starting, we got a different number. It doesn't sound like a big deal at first. Based on what we see today, every 3 million light-years away, things are moving about 40 miles per second faster. But based on how our universe was supposed to develop, the number is about 45 miles per second. Literally just 4 miles or so, right? But in cosmology, it's an ultimate red flag. The error bars have shrunk so much that now this isn't just a meh, probably fine situation. It's a literal tension in measurement. And that's exactly what scientists call it, the Hubble tension. It's a serious difference between two super precise measurements based on very different methods, and both of them seem equally right. Imagine using two ultra-precise clocks to check how fast an athlete runs a distance. And in the end, one of the clocks says 10 seconds, while the other says 11. What in the world does that mean? That's terrifying. The two numbers should match, and since they don't, one of three things must be true. First, maybe one of the measurements is wrong, which is very unlikely because both methods are super reliable. Second, maybe something in our interpretation is wrong, but that's also unlikely since many scientists get the same result and agree that the tension is a real deal. And finally, the scariest option? Our entire model of the universe is missing something. That's why scientists are freaking out, and as it turns out, they had a reason to. Recently, a new research team from Hawaii proposed something wild. What if the universe is very slowly rotating? If that's the case, it would be absolutely insane. Here's why. First, if the universe actually rotates, even super slowly, it would mean that the laws of physics might be slightly different depending on where you are or which way you look. That breaks one of our most sacred ideas about physics, that space is the same in all directions. Second, it could mean we've misunderstood the entire cosmic history. Maybe we don't actually know how fast the universe is expanding when it was born, or what dark energy is. That would be a huge disaster. And finally, the most horrifying of all, if it's spinning, then it must spin around something, right? If there's a cosmic axis or rotation, it might suggest a preferred direction. It would be something like cosmic north. We thought there's no special place in the universe, but we might have been wrong. Maybe there's a special place after all. It's like finding out the reality itself has been tilted a tiny bit the whole time, and we just noticed. Right now, we're in an exciting and scary place. Either we'll discover new physics and maybe something about dark energy, or we'll find a subtle error in one of the measurements. Or who knows, maybe something totally unexpected will show up. In any case, solving the Hubble tension could revolutionize our understanding of the universe's origin, structure, and our place in it.
For decades, time travel has been dismissed as impossible. But this physicist just cracked the code using quantum mechanics. He's trying to prove that time loops might actually exist without breaking reality. So could this be the first real step toward building a time machine? In everyday life, we're used to time moving forward in a straight line. It goes from the past to the present to the future. That's how people saw it before Einstein, because that's how it feels to us. But when Einstein showed up, he told a very different story. He showed that both space and time are woven together like some flexible fabric into one thing called space-time. Space itself can bend and twist, and time does the same with it. The fabric of space-time bends and gets curvy when we place heavy objects in it, like planets, stars, or black holes. The heavier the object, the more it will get stretched and bent, slowing down time around it. Movies like Interstellar showed it pretty well, even though the characters only spend a few hours on the planet. When they return to the spaceship, 23 years have passed for the astronaut waiting there. Why? Because the black hole's extreme gravity warps this fabric of space-time itself, and the closer you are to it, the slower things go for you. Sounds insane, but that's how our universe works. And that's not just black holes. All massive objects, like the sun, for example, bend the fabric of space-time around them. This is also why planets orbit in curves. All this gave physicists a pause. If we can bend space-time, can we bend it to such a way that we'll make a loop out of it? It would be like going on a journey that bends back on itself, meaning that if you followed it, it could return to the past and experience the same moments again. That would be pretty insane. Imagine that you walk down a hallway expecting to exit through the door at the end, but instead of a door, you find yourself standing right back where you started, walking into your past. But just imagine how hard something like that would be to pull off. Yes, heavy objects can stretch and twist space-time, but even those massive things still don't loop time. They just slow it down very strongly. It's hypothetically possible, but it would require super extreme conditions. For example, if the black hole gets a little extra boost, spinning, it could theoretically bend space-time around it into a loop. There are also some wacky ideas, like exotic matter and wormholes, but they're all speculative. But let's assume that there is a way to make a CTC. Creating it isn't our only problem. This is where the paradoxes begin. If a time loop could exist, wouldn't it create contradictions? The grandfather paradox is just one example. If you follow a big loop like that and accidentally prevent your grandfather from meeting your grandmother, you'll make it mean that one of your parents is never born, and you weren't born either. So how could you travel back in time in the first place? Or what happens to you after that? There are other ideas like that, like destroying your time machine before you use it, or giving William Shakespeare his own plays. There are infinite possible paradoxes. All this is happening because of entropy. It's one of the main laws of physics, this idea that chaos in the universe always increases. Things start as something normal and structured, but eventually they break apart, becoming weird and chaotic, and can never go back. Ice melts but never refreezes into its original shape on its own. Our bodies age instead of getting younger. We remember the past, but not the future. All these are examples of entropy. So, like, if time travel were possible, how would entropy behave? Would a broken glass fix itself? People would grow younger, and people would lose their memories? That's exactly how paradoxes like grandfather's paradox are born. Well, this is where the recent theory changes everything. The physicist Lorenzo Gavasino has a cool idea to explain this issue. He tackled quantum mumbo-jumbo, working with something called quantum fluctuations. See, the universe is never completely still. Even in empty space, at the tiniest level possible, there are constant random changes in energy. These are those quantum fluctuations. They're like tiny, unpredictable jitters that pop in and out of existence. Yeah, our universe is just weird like that. It's like a lake. On a normal scale, it looks smooth, but if you zoom in super close, you'll see tiny, unpredictable ripples forming and disappearing all the time. Our universe is the same with quantum fluctuations. These fluctuations happen everywhere, and they become really important when dealing with stuff like black holes and time loops. Now, back to the time loops. Gavasino says that in a time loop, quantum fluctuations mess with entropy in a strange way. Ideally, the chaos should increase. As usual, we're getting older, our spacesuit is getting weary, broken things don't fix themselves, and so on. But it seems like instead of always increasing, chaos in a time loop can randomly decrease. This means things that should be irreversible, like aging or breaking something, could actually reverse themselves. So yep, if you try doing something wild during time travel, it won't really work. If you try to prevent your grandpa from becoming your grandpa, the universe could reverse that change, making it like it never happened. If you travel to the past, your memories could vanish, meaning you wouldn't remember the future you came from. And if you try to break causality, the universe might just remove the contradiction. Time would always find a way to correct itself, preventing paradoxes. Scientists actually suspected this for a while now. Many of them have believed that if time travel were possible, the universe would somehow prevent weird paradoxes. Basically, it would make sure that everything that happens must be logically consistent with itself. Well, Gavasino's work basically gave a mathematical proof of that using quantum mechanics. Of course, there was another wild theory, the one with multiple universes. You definitely saw this in the movies. It says that when we travel back in time and change something, we simply create a new timeline. The old one remains, but this one would go a completely different way. But this idea is more about cool sci-fi than actual math and physics. But does that mean that time travel actually exists? Well, not right now. Even if time loops could exist in theory, that doesn't mean they actually do exist in real life. Stephen Hawking, for example, thought that these time loops are impossible. He said that the universe works in such a way that it would simply prevent time loops from forming. He even organized his famous time traveler party. Unfortunately, no one showed up. But many physicists still believe time travel is impossible, at least on a macroscopic scale. They even kind of managed to do that. For example, teams from Oxford and Vienna wanted to see if they can reverse one single electron back in time, and they managed to do that inside of a quantum computer, though the effect was tiny, only a fraction of a second. Recreating that normally would be absolutely insane. If we wanted to see something like this naturally, we would have to observe 10 billion electrons per second for the entire age of the universe. And even then, we'd only see it once. The more particles they tried to rewind, the more errors appeared. With one tiny electron, it worked well, but when they got to 3, accuracy dropped in half. But even if we never find a way to travel through time, understanding all these things could still help us a lot. It would help us study black holes, the early universe, and even quantum technology. So, while time machines are still science fiction, this research is pushing us closer to understanding our universe. You may have time traveled multiple times already. You just don't remember it. A recent study says that all your memories of the trip would be completely erased as soon as you're back in the present. And you can blame it on something called entropy. To explain it, we first need to talk about closed timelike curves, or CTC. This is a closed path where a particle could travel, and it ends up right back at its starting point, at the exact same time it left. In other words, it's like a cosmic time loop. Take this notebook paper. Picture each line as a different timeline with a beginning, a middle, and an end. Now, if you roll that sheet of paper, the lines connect. Suddenly, they form a continuous line with no beginning or end. That's what CTCs are, closed timelines that don't have a starting point. Past and present blend together in an eternal time loop. Now, a more practical example. You're taking a walk around a park. A woman jogs past you, and a dog starts barking. You keep walking, but then, wait a minute. You realize you're back at the exact spot where you started. The same woman jogs by, and the dog barks again. But here's the thing. It's not just that you've returned to the physical starting point of your walk. In a closed time-like curve, you're retracing not only your steps, but every single second of reality itself. Alright, now think about the big moments in your life. Being born, graduating from college, getting married. If all these events are part of one big time loop, that means time travel is possible. It sounds crazy, but there's a concept behind it called the self-consistency principle. It says that time travelers can't create time paradoxes. I mean, time travel can't just be this wild, chaotic mess like those crazy butterfly effect scenarios. Even if you go back in time, everything in your life still has to fit together in a way that makes sense and lines up with what we already know today. I'll explain. Let's say you go back in time and stop your mom from meeting your dad. But here's the problem. If they never meet, then you wouldn't exist. And if you don't exist, how could you have gotten into the time machine in the first place? That's a time paradox. That's why time travel could only work within these closed timelike curves. No matter what you do, the past, present, and future are locked in. They're always going to play out the same way, like a loop. Okay, so now you understand what CTCs are and why they're important for time travel to make sense. Now, we can finally talk about entropy and why it's probably the reason we'd lose our memory after a trip to the past. Entropy is a way to talk about disorder, chaos, or randomness in a system. Imagine a super clean, minimalist bedroom where everything is neatly arranged. Everything's in order. That's low entropy. But then, picture a messy teenager moving in. Every day, clothes, books, and random stuff gets scattered around the room. It's a mess. That's high entropy. In nature, things usually trend toward more disorder unless you actively work to keep them organized. Like this ice cube. It's made up of water molecules, all neatly lined up in perfect order. Low entropy. But if you take this ice cube out of the freezer, it will melt into water. See how the puddle looks messier now? In this form, the water molecules can be arranged in so many different ways. They're all disordered and random. And that's higher entropy. If we apply this idea to time travel within a CTC, the closed time loop, things get even more interesting. According to specialists, a key feature of this circular journey is that the level of entropy has to be the same at both the beginning and the end of the trip. Here's an example. You're just living your everyday life. Nothing too exciting going on, so the entropy level is low. But then, you get inside a time machine and go back to the past, right before you broke up with your high school sweetheart. By traveling through time, the chance of you changing the past and totally throwing your story into chaos is pretty high. Let's say you don't break up with her, and in this second chance, you decide to propose to her. See how everything could go totally sideways, right? So, when you go back to the past, the entropy is at a super high level. Now, you get to the exact moment when you're about to talk to your past love. At that point, entropy is at its peak. You're about to kneel down, show her the engagement ring, when, well, here comes the self-consistency principle, and it throws a cold bucket of water on this whole romantic idea. Remember, in a closed time-like curve, nothing can significantly change the present reality. All the changes a time traveler makes in the past can't cause any historical paradoxes. So, sorry to say, but you're not going to end up with her anyway. You decide to hop back into the time machine and return to the present. You get back into your routine, your job, and well, your single life. After completing the time loop, your timeline is back in order. Now, the level of entropy is low again, just like it was at the beginning of your journey. It's like you did a reset on the system. And that's the bad side effect of all this. Pressing this reset button would probably erase all your memories of the trip by the time you get back to the present time. Unlike in the movies, a time traveler probably won't recall anything. What? Now, answer in the comments. Even if you can't remember what you did after going back to the past, would you still take the risk? I'm guessing your answer would be, yeah, of course. That would be my answer too. After all, we could bring our phones and still make tons of cool photos on this trip, right? Well, no. This is where the laws of physics crush our hopes. Again. The second law of thermodynamics says that in an isolated system, entropy, or disorder, tends to increase over time. But this doesn't apply only to humans, but also to non-living things. It's why you can't unscramble an egg, unmix coffee from milk, or take your phone into a time machine. If a time traveler stores any data on their smartphone during their journey, experts believe it will probably get wiped out as soon as the trip ends. All the videos, photos, poof, gone. That's because machines probably wouldn't work properly when we go back in time. For example, let's say you bring a classic analog watch with you. For all the reasons we've already talked about, when you come back to the present, the clock needs to be exactly where it left off. I mean, the clock hands should be in exactly the same position at the beginning and the end of your journey. But to make that happen, it's likely that the frequency and number of ticks during the trip will be different. That could cause small problems in clocks made for regular time, making them unreliable. Something similar could happen with your phone. Its system probably wouldn't work as it should. All these consequences of time travel were described in a study by a mathematician published in 2024. While his theory doesn't determine whether time travel is actually possible, it does point out the strict conditions that would have to be met. And, well, it seems like having a time machine at home might not be as great as it sounds. In the end, you wouldn't remember a single thing about your amazing trip, and you'd probably just end up exactly where you are.
Time is nothing but a magician's trick. Or is it? We're used to time zipping along like a car, always pointing into the future. It creates cause and effect, lining events up one after another, like dominoes. Sometimes it stretches between moments, getting so slow it might even want to stop. And it's got a spotlight on right now, because that's the only moment that truly matters. But there's a new theory that it might not exist at all. We usually think of space as having three dimensions: up and down, left and right, forward and back. And everyone thought that time was a separate thing, just a universal clock ticking away in the background, and it's the same for everyone. But then Einstein came forward. He decided to surprise everyone back in 1905 when he introduced his special theory of relativity. It said that time is another dimension, just like the others, and they're all tied together in one big space-time. Based on this, it turned out that time can change depending on the speed at which you move. Now imagine that we take two twins. Twin A stays on Earth. Twin B takes a journey into space on a spaceship moving at a speed close to the speed of light, let's say 90% of that speed. Twin B travels to a distant star and then returns to Earth. For Twin B, it feels like the journey only took a few years. But when they come back to Earth, it turns out that Twin A has aged significantly more. They find out that 20, 30, or even more years have passed on Earth. That's all because of the phenomenon called time dilation. It happens when we're reaching speeds close to the speed of light, causing time to slow down for the traveler relative to someone who stays in one place. 10 years later, Einstein proposed his theory of general relativity. That's when we learn that time changes not only based on your speed, but also based on gravity. Back in the day, Newton thought that gravity was some magical force that makes objects attract each other. However, Einstein proposed that this isn't a force, but more like an after effect. Picture the space as some huge cloth. When you throw a heavy ball on a cloth, it curves. Now, if you throw some small balls around it, they will naturally approach the heavy ball. At the same time, massive objects like stars and planets cause space-time to curve around them. When there's something super heavy in space-time, it curves the matter around it. This curvature tells objects how to move, and this is what we call gravity. This idea created all sorts of cool predictions that later turned out to be true. Bending of light by gravity, black holes, and time dilation around these black holes, just like in Interstellar. This theory revolutionized our view on everything, but we might be on the verge of another revolution. Some philosophers have a crazy claim. They say that the things we believe about time are all just ideas in our heads, not facts of the physical world. This idea, which breaks the traditional view of time, is called the block universe. It's backed up by Einstein's theory of relativity, but extends it and makes it more complicated. Imagine the universe as a huge sandwich. This sandwich contains every moment of time, past, present, and future, all at once. Each layer or slice of the sandwich represents a different moment in time, and all these layers exist simultaneously rather than one after the other. In this model of our world, the past, present, and future are all equal. Unlike our everyday experience, where the past is gone, the future hasn't happened yet, and only the present is real, the block universe says that every point in time is just as real as every other point. Imagine your birth, this moment right now, and what you'll be doing in 10 years from now, all exist together in this block. It also says there's not really a flow of time. We're used to time flowing from one moment to the next, even with Einstein's theory. But in the block universe, the feeling of time moving is more about how we experience and remember events than about how time itself works. It's like reading a magical book. All the pages exist at once, but you can only experience the story page by page. Now, this implies some scary things, like destiny, and whether free will actually exists. If everything is already laid out, does what we do matter? For example, you clicking on this video was already predetermined in the block universe. Every choice you've ever made was an illusion. You're just a program following a code, but with an ability to understand its consequences. This would explain why we order junk food at midnight, knowing that it's a bad idea that we're going to regret. But some scientists argue that time's flow and direction are as real as it gets, because cause and effect still exist. If your birth, current moment, and you in the future with gray hair all existed at the same time, you'd be able to visit your past self at any moment, and already knew what your future self is like. So this whole debate might just be about how we piece together our stories of the past, not proof that the future isn't waiting to unfold. There's also a never-ending battle between general relativity and quantum mechanics, which only adds spice to the debate. On one hand, general relativity plays with time like it's a stretchy Play-Doh. The flow of time can stretch or compress depending on the speed or gravity. On the other hand, in quantum mechanics, time isn't something that can be manipulated or changed. It's a constant stage upon which the particles and forces of the universe perform. These two fields have been fighting for a long time now, and scientists are struggling to unite them in one cohesive theory of everything. Although there are some candidates who try to merge them in a logical way, like string theory. Now, string theory sounds scary, but it's simply saying that the entire universe, with all its particles and atoms, is made up of ultra-tiny vibrating strings. Each string can vibrate in separate ways, like the strings on a guitar, and in many dimensions. The way these strings vibrate determines what type of particle they will be, like an electron or a quark. Another idea, called loop quantum gravity, says that space and time are made of tiny loops. Whether it's strings or loops, unfortunately, they would be so tiny that we simply don't have strong enough equipment to check them out yet. So until we test these theories, they can't be proven. What's interesting is that both ideas don't really need time to explain how the universe works. We think of things like tables and chairs as real, even though physics doesn't describe them directly. We say they emerge from the tiny particles that make up the universe. But with time, we're not sure how it would emerge from something else. But no matter what the answer is, you're going to be okay. If it turns out that it doesn't really exist, then it could make everything feel pointless. But think about this. We still lead our lives, and we still experience what feels like causation and make sense of everything. It still feels like it was our choice to order that junk food at midnight. So, does that being predetermined really matter? In any case, we've been wrong about plenty of things we thought were set in stone. Right now there's a big split between the block universe and our traditional theories. But we'll learn the truth over time.
Turns out we have some ways to solve the time travel paradoxes. Time travel sounds enticing, but brings with us a lot of problems. Take, for example, the famous grandfather paradox. Imagine that you travel back in time and prevent your grandparents from meeting. This alters the course of history. But how? If you erase their encounter, you cease to exist, so you couldn't even travel back in time to alter the past in the first place. There's also the bootstrap paradox. Let's say we travel back in time and give Beethoven his own compositions before he ever penned them. He gets famous for the very music you provided. But where did it originate? Did you start it? Or was it Beethoven who started it? There are many theories about time travel. One of them involves alternate timelines and parallel universes, like in Back to the Future, for example. If parallel worlds exist, we could hypothetically travel in one where the events unfolded differently, while our original timeline stays the same. This is a beautiful and paradox-free approach, but this is pure sci-fi, as we have no concrete evidence of parallel universes. So what scientists are trying to do instead is to figure out whether time travel is impossible in this one universal timeline. We've been exploring this equation for over a decade and created a fascinating concept called a closed timelike curve, or CTC. Imagine taking a path that forms a loop, bringing it back to where it started, but in time. We know that space-time is like a wobbly piece of cloth which can curve and bend when we place heavy objects on it. In some situations, like near massive objects such as stars or black holes, space-time can be curved. Now, imagine an object that's so heavy, with gravity curving the space-time so strongly that it literally loops on itself. If this idea turns out to be real, it could suggest the possibility of traveling back in time in our world line. This possibility is fascinating, but it also creates tons of problems, and scientists may have found the ways to solve them. One of the solutions is that doing paradoxical things can be simply impossible. In this scenario, we assume that the universe has some mechanisms of self-consistency. It means that while you can still travel in time, you're restricted in the actions you can take. For example, you may not be able to go back and alter your family's history, but there's nothing inherently illogical about traveling back in time to simply interact with your ancestors. In this scenario, the universe only forbids you to do logically impossible things. Scientists decided to conduct an experiment to check if it works, and the results were pretty terrifying. The experiment conducted involved the creation of a theoretical time machine. This is also called an in-principle time machine. This wasn't a physical device, but rather a quantum simulation. In the simulation, they attempted to send a photon back in time by a fraction of a second and make it interact with its past self. The goal was to find out what the photon will do. Will it destroy its previous self, avoid the interaction, or something else? What happened is that as the photon approached its past self and was getting closer to the point of creating a paradox, the experiment tended to fail more frequently. In other words, it seems like the laws of physics or the fabric of the universe might have some weird built-in mechanisms that prevent time travel paradoxes. In that case, the question is, how does the universe understand what is logically impossible? And how does it prevent us from doing these things? Which is quite scary to think about. There's another theory that the universe allows paradoxical things to happen, but also self-corrects them. Imagine a time traveler going back to stop some health condition from spreading. According to this theory, even if the traveler succeeds, this health condition would find another way to spread, avoiding the paradox. Or maybe we all exist in time loops. These loops allow objects to interact with their past selves while still maintaining a consistent timeline, because there's no beginning point. For example, trying to prevent a historical event could result in accidentally catalyzing the event we were trying to prevent. This idea challenges our understanding of classical physics and free will. But all these ideas are purely theoretical, and to test them, we first need to find the mechanism to actually travel back in time. Talking about practical time travel, we mentioned that space-time curves around very heavy objects. Does it mean that black holes can be portals to the past and the future? Maybe. Black holes are formed when a massive star collapses inward. Their gravitational pull is so intense that even light can't escape. This means they're perfect for bending not just space, but even time itself. You might remember this from Interstellar. Near a black hole, time slows down. This effect is so pronounced that a year near a black hole could translate to decades on Earth. In that case, traveling back to the past using a black hole is theoretically possible. If their gravity twists time so much that it wraps back on itself, creating a closed time-like curve, and you could enter this loop, you'd find yourself on a journey from the future to the past. But there are some problems with this. First, you can only travel into the black hole's past. Second, to enter the loop, you'd likely have to cross the event horizon, the point of no return around a black hole. To escape one, you'd have to travel faster than light, which is currently impossible. So, while black holes might hold the keys to time travel, the journey inside one might be your last. But not everyone agrees that closed time-like curves exist at all. Recent research has shed new light on this topic. The results showed that time can only move forward. The research offered a fresh perspective on how light behaves when it encounters different materials. When light moves through empty space, it travels at a constant speed of 186,000 miles per second. But when it encounters substances like water or glass, its speed can change, causing it to bend or refract. While scientists have equations to describe this behavior, they struggled with the problem of the change of the speed of light at the boundary in different mediums. Well, researchers proposed a solution to this puzzle by reconsidering how light moves through time and space. They figured out that it always remains constant as it travels through different mediums. No matter what the light encounters, it always moves forward in time. This means that light and other waves like it follow the same one-way path through time that we do. Another thing is that light also always saves its momentum, and it always stays the same, pointing forward in time. And finally, even with general relativity and with gravity bending light very strongly, it still keeps pointing forward. It can slow down to the point of feeling like time stopped, but never move backwards. This challenges our previous notions about the relationship between light and time. It implies that time has a definite direction for all waves, making it impossible to reverse. However, their equations have only been tested in one dimension, and experiments are needed to confirm if this theory holds true in reality. Stephen Hawking also disagreed with the idea of traveling back in time. He proposed a theory called the Chronology protection conjecture. This idea says that the laws of physics stop time travel on large scales, even when theories like general relativity say it's possible, and that closed time-like curves simply can't exist. Hawking said that traveling back in time would mean creating new matter, which goes against the laws of physics. Although we're far from building actual time machines, if we keep diving into mathematics, we might find the truth one day. We're about to embark on a journey into the realm of faster-than-light travel and the wacky time paradoxes that come along with it. Is it possible to travel faster than the speed of light? What exactly happens when you do it? And why does it lead to time paradoxes? Buckle up and let's figure it out. First of all, let's discuss the concept of faster-than-light, or FTL travel. This idea has captured our imaginations for decades. It's been the driving force behind some of the most beloved space adventures in popular culture. Just think of the iconic Star Trek series, where the USS Enterprise and its crew boldly go where no one has gone before, thanks to their warp drive technology. Or how about the epic Star Wars saga, where ships like the Millennium Falcon are defying the laws of physics with their hyperdrives? FTL travel is the key to exploring distant galaxies and discovering new civilizations. But here's the catch. In the real world, our current understanding of physics, as described by Albert Einstein's theory of relativity, puts some serious limitations on FTL travel. Picture this. You're cruising in your FTL spaceship, zooming through the galaxy like a rock star on an interstellar tour. And you start accelerating and going super duper fast, almost at the speed of light. It's crazy fast, by the way, around 186,000 miles per second. But according to the theory of relativity, things start to get funky when you do that. Time starts playing tricks on you. This crazy phenomenon is called time dilation. It's when time slows down relative to an observer as speed increases. The faster you go, the slower time seems to tick from your perspective. Yep, you heard it right. Basically, time slows down for you, and while you might experience just a few seconds on your super fast journey back on Earth, years could have passed. So let's say you have a friend on Earth who's patiently waiting for your return. While you're out there exploring the cosmos at breakneck speeds, your friend might age significantly more than you. When you finally return to Earth, you might find that they've turned into a wise old sage while you're still fresh as a daisy. And here's the crazy part. Time dilation has actually been proven. It's not just science fiction, unlike FTL travel. Scientists have observed time dilation effects with super fast particles zooming through particle accelerators. We encounter this concept much more often than you think. It's crucial in our everyday lives, especially when it comes to our trusty GPS systems. Those satellites high above us are zooming around the Earth at crazy speeds. And guess what? Their clocks tick just a tiny bit slower than ours down here. So, to make sure your GPS can navigate you to that funky restaurant downtown, scientists have to take time dilation into account. It's like a secret time traveling equation behind the scenes. But why does this happen? Well, according to Einstein, as you move faster and faster, the fabric of space and time itself gets all twisted and distorted. Imagine you're on a trampoline and you place a heavy ball in the middle. The trampoline stretches and creates a dent, right? In a similar way, Einstein's theory tells us that when you move really fast, like zooming through space, you create a dent in the fabric of space and time. Yep, you're like a really heavy ball, and the fabric of space-time itself gets all twisted and distorted, just like the trampoline. But here's the catch. The theory of relativity also tells us that as you approach the speed of light, the amount of energy required to keep accelerating increases dramatically. It's like trying to push that heavy ball on the unterrible trampoline harder and harder. It gets more and more difficult. Also, as you get closer to the speed of light, your mass appears to increase. So, it's like becoming an even heavier ball on the trampoline. And of course, this would make accelerating even harder. That's why, according to Einstein, the speed of light is the ultimate speed limit. It's like a cosmic barrier that nothing with mass can surpass. But it never hurts to try, right? So let's have some fun. So, why is time dilation so important when we talk about faster than light travel? Well, if we ever figure out a way to go faster than light, this phenomenon would come into play big time. It will start causing us some trouble by creating time paradoxes. Time paradox is like a cosmic brain teaser. Imagine you stumble upon a time machine and decide to travel back in time. You arrive at a moment in history where you encounter yourself. It's like looking into a mirror, but instead of your reflection, you see your own past self staring right back at you. Now, here's where things get wibbly-wobbly. You decide to give your past self a high five. But wait a minute. If you high-five your past self, who initiated the high five in the first place? It's a mind-boggling loop that seems to defy the very concept of cause and effect. Welcome to the magical world of time paradox. It's basically a twisty-turny situation where the cause and effect of an event becomes all jumbled up. One of the most famous time paradoxes is the grandfather paradox. Imagine you decide to use your time machine to go back in time and accidentally prevent your own grandparents from meeting. As a result, your parents are never born, which means you can't exist. But if you don't exist, how could you have gone back in time to prevent your grandparents meeting in the first place? It's like a cosmic puzzle where the pieces just don't fit. There's also the bootstrap paradox. Imagine you travel back in time and you decide to give Beethoven his own compositions before he even writes them. He becomes famous for that very piece of music. But where did it actually come from? Did you compose it, or did you receive it from Beethoven? It's a mind-bending question of origins that keeps you guessing. Time paradoxes challenge our understanding of cause and effect and tease our logical minds. They make us question the very nature of time itself. So, why does FTL travel lead to time paradoxes? Well, if we could somehow travel faster than light, we would effectively be breaking the cosmic speed limit and violating the laws of physics as we currently understand them. This opens up a can of temporal worms, so to speak. Now, it's important to remember that the current scientific consensus is that FTL travel is highly unlikely, at least based on our current understanding of physics. The theory of relativity has been tested extensively and has held up really well. It's provided accurate predictions and explanations for almost everything. Almost. That doesn't mean we should stop exploring the concept of FTL travel or dreaming about the possibilities it holds. Science fiction has always been a playground where we can stretch our imaginations and inspire future scientific advancements. So folks, let's take a fun and simple dive into the real-world implications of FTL travel. Getting over the light speed limit means zipping through the cosmos faster than anything. Zooming past galaxies, exploring distant planets, and having a blast with your extraterrestrial pals. Scientists are always exploring new frontiers and pushing the boundaries of our understanding. They're constantly dreaming up new theories and concepts to explain the mysteries of the universe. So, do they have any ideas on how we can get over the speed of light? Actually, they do. For example, one intriguing idea is the concept of wormholes. These are like shortcuts that could potentially connect different parts of the universe. If we could harness and control these wormholes, it could open up possibilities for FTL travel. It's like having a highway system that bypasses the usual laws of space and time. Just be careful not to miss your exit. So, while FTL travel remains firmly in the realm of imagination and theoretical speculation for now, it doesn't dampen the spirits of exploration. Our universe is a vast playground of wonders waiting to be discovered. So, keep dreaming, keep exploring, and keep your eyes on the stars.